from Sangmin on momentum twistors for relativistic spinning particles.
Thanks. Yeah, so continuing from my last lecture yesterday, I'm still thinking about a gravitational binary, and in most of these works, we are treating the celestial bodies like black holes, neutron stars, or maybe even ordinary stars, as if they are point particles. Well, of course, they are not point particles, but if the typical length scale, like the wavelength of the gravitational wave, is much longer than the actual size of the star or a black hole, then it's it can be a reliable approximation. So, in this point particle viewpoint, the leading degrees of freedom is, of course, the position and momentum, but you can think of adding some additional degrees of freedom, and one of the most well-known and well-studied is the spin of the particle, because all those stars and black holes are actually spinning. So how do we add spins to a relativistic point particle? I'll spend most of my time talking about a free particle. So let's go back to an early stage of our education as a physics student. So in Newtonian mechanics, when we have a point particle, this is the Lagrangian that describes the dynamics. And we also learned how to add spin. Well, in the simplest case of a spherical top, it's just the angular velocity square multiplied by the rotational inertia. When we learn special relativity, we learn this beautiful fact that the Lagrangian the action for the point particle in special relativity is just the proper length of the trajectory. So the question is, how do you combine these two things to get an action in special relativity, which includes spin in the simplest manner? I'm pretty sure you haven't seen this in any textbook. Well, I looked up many books, but I couldn't find any. But of course, the problem itself has been around for a decade. So the oldest paper I looked up is from 1920s, but rather I was somewhat surprised to notice that the problem took a long time to be solved. Well, it depends on what you mean by the problem is solved, but in my personal viewpoint, I think the decisive work, which sort of combined all the previous work and laid down the foundation in a firm way, was the one by Hansen and Raju from 1974. So yeah, I'll spend some time talking about this model. So the basic ingredient of Hansen-Raju's spherical top model is to introduce the position variables and momentum variables in a relativistic covariant manner. So X and P part is kind of obvious. For the rotational degrees of freedom, we want the relativistic generalization of the Euler angles and the associated angular momentum. So we write down the obvious index structure compatible with the symmetry. So X and P take values in the Minkowski space. And this lambda, which you may think of as a body fixed frame, is an element of SO 1,3 group. And as mu nu is an element of the Lie algebra of SO 1,3. And the time derivative of lambda gives you the relativistic version of the angular velocity. So it looks perfectly covariant. So can you just write down some, Lagrangian or Hamiltonian for the dynamics of these variables? The main complication comes from the fact that these variables have more degrees of freedom than what we need. I mean, going to the relativistic setup doesn't mean that the number of degrees of freedom changes, right? So here we know that we have 3 translation degrees of freedom and 3 rotation degrees of freedom. And we want to keep that. But for the translation part, we know how to deal with the extra degrees of freedom. I mean, we impose the Mastrial constraint to reduce the number of the independent momentum. And we also recall the fact that on one of these axes is correlated to the proper time of the of the particle trajectory. So the true number of degrees of freedom is 3, even though apparently we have 4 x's and 4 p's. Excuse me. So we need some way to reduce the number of degrees of freedom from the apparent 6 down to 3. And the rough idea is that, the Lorentz group element contains 3 rotations as well as 3 boosts. And the boost degrees of freedom are not real. I mean, the real degrees of freedom are only for rotations. So we want to kill the boost part. But there is one technical obstruction, that is boost generators. If you just take them naively, then they don't form a closed algebra. So yeah, that I think is the main reason for the complication. Anyway, we want some constraints for spins, and people from the old days took this seriously and did a lot of work. So if you look up the literature, you find a few different options. How do you kill 3 out of, say, 6 components of S mu nu? There are several different candidates. So one is you take the time part of the body frame and require that the component of the spin along that direction should vanish. And a similar, but not quite the same requirement is to use your momentum vector as the reference direction and killing the component of the spin in that direction. And actually there is one that's sort of intermediate step between the two. And this combination arises from the work by Price, Newton, and Wigner between 1948 and 1949. And well, I must add that this is just not a random linear combination of the two. There were some serious reasons for considering this particular combination, but I don't want to repeat all the old stories and jump directly to a modern viewpoint of the same observation. So, I mean, everything was already in Hansen Raju paper, but there are ways to slightly rewrite their result so that things are even more clean and streamlined. So yeah, we learned this viewpoint from a paper by Steinhoff in 2015, and we modified it a little further. And a key idea is to separate the constraints into gauge generators and gauge fixing conditions. And let me specify what I mean by that. So for the gauge generators, I use the letters phi, and with the label 0, I bring up this mass-gel constraint. And when you take the Poisson bracket between this guy and the coordinate x, then you get something proportional to p, and shifting x by p is the translation, right? So in that sense, this is the translation generator, and in empty space, translation is a symmetry. Now, we want gauge generators for the rotation, related to this rotation part. And yeah, by improving upon the work of Steinhoff, we realized that this slight modification of the Price-Newton-Wigner spin condition is the best way of writing it. So this is a spatial part of the body frame. This is the temporal part, and this is the momentum direction. And it's sandwiching the spin tensor. I know if you first look at it, it doesn't ring a bell. You don't get a good intuition. So, that's consistent with the fact that people took a long time to land on this. But the final message is pretty simple. Although this phi 0 and this phi a are not related by any symmetry, I'll just combine them as if they are 4 vectors. It's an abuse of notation. No real symmetry there. But anyway, if you compute the Poisson bracket of any of these guys, they all vanish. So even though we know that the boost generators in the literal sense don't form a closed algebra. This particular combination actually do form an algebra, well, an abelian algebra. And this observation makes the following steps fairly simple. And if we want to keep the best, keep the nice features of Hamiltonian mechanics all the way, we want a balanced pairing of momentum-like variables and space-like variables. And we treat these gauge generators as momentum-like variables, and we want to pick the corresponding position-like variables. And the position-like variables are these gauge fixing conditions. And for the gauge fixing conditions, let me list two possibilities. One is the covariant one, where this phi0 is paired with x mu p mu. So it's roughly the time of along the straight line trajectory. And for the rotation part, we are basically requiring that the momentum vector is orthogonal to the spatial part of the frame vectors. This is covariant, and this is very natural. And another thing is, if you demand all the constraints, both gauge generators and gauge fixing conditions vanish, then you actually land on this covariant spin condition. I mean, yeah, imposing both of these conditions forces this time frame vector along the momentum direction, so they actually collapse onto each other, and whatever remains enforces this covariant spin condition. I'm emphasizing this point because some people try to use this as the basic building block of the constraint in the sense of Dirac's theory of constraint Hamiltonian mechanics. But if you pick two components out of this combination and compute the Poisson bracket, they don't commute. So you begin to generate many things that you have to worry about. But if you use this particular choice of constraints, the final answer is what you wanted from the beginning, but you don't run into the complication of producing an algebra of generators not closing onto themselves and so on. So as far as I know, this is the best way of packaging the constraints of this system. Well, gauge fixing conditions, but on the other hand, have more freedom. So let me mention what we may call a lab frame. So suppose you have some inertial frame, particular inertial frame for your experiment. For example, for a binary system, although we haven't really turned on any interaction yet, for a binary system, one natural choice is, of course, the center of momentum frame, but you can choose any other reference frame. Then let L be the time-like unit vector, which defines your lab. And for the gauge fixing condition, you can use, for example, so this x dot L is the time in the lab. And you can require that the frame vectors the spatial frame vectors should be orthogonal to this time direction defined by the lab. Well, in my talk yesterday, I mentioned the post-Minkowskian expansion of an effective Hamiltonian and then moved on to a more covariant notion of classical iconal. But for whatever reason, if you're interested in computing an Hamiltonian, you often choose a lab frame and then work there. And when you compute the effective Hamiltonian for spinning binaries in a lab frame, then this is often the most convenient choice. And yeah, one major difference between these two choices is that if you incorporate the effects of the constraints using Dirac bracket, the spin vector in the covariant gauge fixing, computed with the Dirac bracket, doesn't vanish, whereas here, effectively, everything becomes three-dimensional. Well, sorry. Yeah. So on this left side, you get what you expect of the three-dimensional non-relativistic angular momentum algebra, whereas here you get something more complicated, which I don't fully recall. So once you have the right variables and right set of constraints, then it's not too difficult to derive the equation of motion. Well, we are in free theory, so you sort of know the answer for the solution to the equation of motion, even before writing down the equation of motion. Anyway, for the action in the first order formulation, so this omega mu nu is the angular velocity out of these frame vectors. And following Dirac, we put these constraints, the gauge generator part of the constraints, into the Lagrangian. And yeah, after working out some details, you do find the equation of motion. So both the linear momentum and the angular momentum of the spinning body are conserved because we haven't turned on the interaction yet. Here, this M prime requires a bit of explanation. In Hansen-Regge spherical time model, M is it's not just a constant, it's a function of the gauge invariant spin magnitude squared. And this prime means taking derivative with respect to this variable. And this functional relation between the angular momentum magnitude and mass is colloquially called Regge trajectory. Yeah, so this spherical time model based on these variables involved a lot of constraints. So, I mean, as far as the counting goes, we started from 10 plus 10 and imposed 4 plus 4. So what am I doing? Let me write it this way. So for the translation and rotation, anyway, the role of the constraints is that they start from, I mean, we start from this big phase space with lots of redundant degrees of freedom, and the constraints kill everything we don't want, and we end up with the physical phase space. And one nice way to describe the physical phase space is to use the Dirac bracket. I mean, so the Dirac bracket allows us to compute the dynamics on the physical phase space without actually solving the constraints by explicit coordinates. And in this particular context, the Dirac bracket is defined this way. And so if you plug in some of your variables in the covariant choice of gauge, then you find a few interesting relations. For example, x mu Dirac bracket produces total angular momentum. I mean, including the orbital part and the spin part inside. And x mu p nu Poisson bracket gives you delta mu nu minus this subtraction of the momentum direction, and everything comes out. Since the gauge algebra of the spin part happens to be abelian, it's actually possible to explicitly map out the gauge orbit. I mean, so the gauge orbit is, of course, not physical, so you have no good reason to be interested in it too much, but, well, since this description is fairly simple, you can actually map out the gauge orbit and confirm that it's safe to systematically get rid of all the gauge orbit and focus on the physical phase space that remains after you impose all the constraints. Yeah, so this was a review of the good old Hansen-Raju spherical time model. And let me move on to, well, any questions so far? So let me move on to the next topic, which is the massive twistor. And this massive twistor is an interesting reinterpretation of this massive spinor helicity variable advocated by Arkani-Hamed and Huang. I suppose this one was from 2017. spinor helicity variables. So yeah, these authors use these variables as a means to express scattering amplitudes involving massive particles in a nice way, somewhat analogous to the massless spinor variables for gluons and gravitons and so on. But in our work, we propose that we use the same looking variables in classical mechanics. I mean, as an alternative to the variables I just erased from here. So what are the coordinates? So I'll label the coordinates with some indices, which will look somewhat similar to what you have seen in other talks of this workshop. Yeah, so in this matrix notation, we have 4 rows and 2 columns. And let me also write down the conjugate variable, which is you take the Hermitian conjugation and also the invariant tensor with signature 2,2. So the symmetry group here is SU2,2 times SU2 times U1. This SU2,2 acts on the left side of this matrix, on this capital AB labels, which can be split into this alpha beta and alpha dot beta dot indices. And anyone who studied the conformal symmetry of Minkowski space, I mean 1,3 dimensional Minkowski space, recognize this SU2,2 as the superconformal symmetry of the Minkowski space. This SU2 acts on the right on this capital IJ index. And U1 is the overall phase of this complex variable. So what's the physical interpretation? I just told you that this SU2,2 is the superconformal symmetry I mean, not super, just the ordinary conformal symmetry of the Minkowski space. This SU2, well, following this suggestion, is to be interpreted as the massive little group of a massive particle. This U1, we don't see any use, so we will gauge it away. So we will need a constraint for this to kill this U1. Yes.
Gauge condition.
Yes.
You had to somehow break the Lorentz invariance by using the.
No. In the lab choice.
Mm-hmm.
Yeah, the covariant gauge fixing preserves all of the Lorentz symmetry.
But you didn't quite do that, right? You imposed the other gauge condition, P mu plus lambda nu 0.
You don't break. I mean, so yeah, even when you use this expression, good. The Lorentz symmetry acts on the mu nu index. This AB index, that's a sort of a fake Lorentz index. There is no real Lorentz symmetry acting on this index. Yeah, sorry for the confusion.
So usually one introduces like a tetrad on the world line to impose these S mu nu and P mu nu constraint, right? In that language, you're not fixing a component of the tetrad or something in that, in the way you're choosing the gauge.
Yeah, let me repeat one thing. That is, so if we require that these phi a's are all 0, and also these chi a's are all 0, and we'll take this p as given, so it's pointing in some future time-like direction, and this requirement enforces the requirement that this lambda with fake Lorentz index in the spatial direction should be all orthogonal to this p, which forces this lambda 0 exactly in the same direction as this p. And since this is vanishing as well, we end up with the conclusion that this is also true. And this is the covariant spin condition that people wanted from the beginning, but somehow got confused because of, there's some constraint dynamics and Dirac brackets and so on.
But if I impose directly that covariant constraint, then you said something goes wrong.
Yeah, well, Dirac's theory of constraints tells you, tells you that you specify your initial set of constraints, and you have to examine the Poisson bracket among themselves to see whether they form a nice algebra. And depending on how it goes, you have to set up the next step of your program and so on and so forth. And if you take this as a starting point, then you don't get a nice algebra. So then most likely you have to throw in some extra factors to improve the situation. And some people tried that and it didn't go too well. But here, everything works in the minimal way, and there's no extra steps to take. These gauge generators, with some choice of gauge fixing conditions, renders a very nice theory where you can do any computation you want.
Thanks.
Yeah, I would say it's a technicality, but it took many decades to resolve all the technicalities somehow. Okay, so yeah, this is the definition of the massive Twistor space. And now our main claim is that, at least for the free theory, if we equip this Twistor space with some Poisson bracket and some other things, then the resulting dynamics is exactly the same as the Hansen-Regis spherical top. Yeah, so we want some map between the Twistor space and the Minkowski space. On this side, we have these variables, lambda, lambda bar, mu, mu bar. Here we have x, p, and s, and lambda. Well, actually, the true physical space is not just the whole space, but the space left over after imposing the constraints. So here we have these i's and chi constraints. Here we will also have some constraints. And our claim is that they should land on exactly the same physical phase space. And to find the correspondence, the space-time symmetry, actually the conformal symmetry, which will be broken by the mass, but I mean, the conformal symmetry is present before introducing the mass. And the symmetry is really the guiding principle. So on the Twistor side, before introducing any constraints, the Poisson bracket compatible with this symmetry is also very simple. And in terms of two-spinor notation with alpha, alpha dot, beta, beta dot, and so on, lambdas and mu's are mutually conjugates. And the SU 2,2 symmetry, which is to be mapped to the conformal symmetry of the Minkowski space, acts linearly on this Twistor coordinates. I mean, yeah, it's literally SU 2,2. So, yeah, the generator of the conformal symmetry acting on any test function can be written as a Poisson bracket between this quadratic generator with F and which generates a vector field on the Twistor space. Like this. Yeah, so to find the map between these Twistor coordinates and the Minkowski coordinates, we want to follow the action of the conformal symmetry generators. And I don't think I'll work out all the intermediate steps, but some results are easy to recognize. So for example, the momentum variable on the Minkowski side is something that all of you have seen many times in several talks. It's literally the spinor-helicity variable, the massive version. So the massless version didn't have this I index. So it was just two-component spinor. In the massive case, it's a doublet of a two-component spinor. So it's like a 2x2 matrix. And so in P square, the mass shell condition translates to the fact that the magnitude of this determinant of lambda should be equal to mass. And we want also the coordinate x and the spin tensor and so on. With the coordinate and the spin tensor or the spin vector through the Pauli-Lubansky map can be read off from what is known as the incidence relation in the Twistor literature. Yeah, so in the original version of massless Twistor by Penrose, he introduced this instance relation as a way to map from the Twistor space to Minkowski space. But when we are dealing with massless spinors, without this doublet index, there can be more than 2 points on this Minkowski space, well, complexified Minkowski space, corresponding to the same mu and lambda. Because, you know, lambda contracted with itself vanishes. But now with this doublet index, to be interpreted as the massive little group, we can actually, you know, multiply both sides by the inverse matrix of this lambda to uniquely determine this z alpha dot beta, which is mu alpha dot I lambda inverse of I beta. So these mu's and lambdas are complex variables. So this z is also a complex variable. Then what are the interpretations? Again, the symmetric consideration shows you that the real part of this complex coordinates can be interpreted as the position coordinate on the spherical top side, whereas this imaginary part can be identified with somewhat normalized Pauli-Lubansky spin vector. Another expression that encodes the same relation, which may be a little bit more intuitive, is J mu nu, which is you know, part of the conformal symmetry generator. Can be written as the orbital part and the spin part, and the spin part can be written as the, you know, Hodge dual of this y wedge p, which is very much like x wedge p for the angular momentum. So although the Twistor coordinates at first sight look quite different from the spherical top variables, if you focus on the gauge invariant combination of both models, they actually agree, and in particular, the you know, symmetry of both systems work perfectly. So we can try to produce the equation of motion, just like we did for the spherical top model. And the Poisson bracket, or the symplectic two form on the Twistor side, more or less determine the action uniquely. But of course, we have to implement the constraints. So we have two real gauge generators and the corresponding gauge fixing conditions. This phi naught is nothing new. It's the mass shell condition written in terms of the Twistor variables. And this phi 1 is the generator of the U1 symmetry, which we didn't want, but was there from the Twistor coordinates. And yeah, you can introduce some gauge fixing conditions for both of these guys. Well, this master condition is common to both models, so there's no mystery there. For the other constraints, the situation is quite different between the two models. Yeah, on the spherical top side, we had true rotation degrees freedom and 3 extra rotation-like degrees freedom we had to kill. On the Twistor side, there is no such thing. I mean, the extra rotation part. Instead, we have this U1 symmetry we don't know how to interpret, so we just decide to kill it. Another consistency check we can do on the Twistor side is to compute the Dirac brackets using these gauge generators and the gauge fixing conditions. And it takes a bit of work, but once you do it properly, then you do reproduce all the Dirac bracket relations, and the relations are exactly the same between the Twistor model and the spherical top model. So we established the equivalence at the level of the free theory. Okay. So it was kind of fun playing with the 2 free models and showing the equivalence between the two. But of course, what we really want is the interacting theory. So how do we couple these special relativistic spinning particle models to background field? So to be concrete, let's focus on the problem of coupling a charged spinning particle to electromagnetic background. So before turning on the spin, well, everyone pretty much agrees that this is the minimal coupling. But if we turn on the spin, the world line action can have some extra terms, like a magnetic field times the spin, or some other more complicated terms. So if we adopt the effective field theory philosophy and start enumerating all possible interactions, you realize that you can have many powers of field strength and many powers of spin, and there is no a priori way to fix their coefficients. Well, it's an effective theory after all. So we usually call these unknown coefficients as the Wilson coefficients. And you can try to fix some of these Wilson coefficients either by comparing with the experiments, or by imposing some extra theoretical consideration into your model. And if you have some sense of simplicity among the possible sets of Wilson coefficients, you may ask what would be the simplest model that's compatible with all the symmetries. So in the world of spinning charged particles, there are some well-known facts. So let me call them, old wisdom. There are several of them. One of them is this equation by Bergman, Telegdi. They showed in a convincing way that no matter how they are from the old generation where the notion of effective field theory as we know it didn't exist. But in modern terminology, they wrote down the universal part of the equation, say ignoring higher order corrections from the effective field theory viewpoint. So up to linear order in spin and linear order in field strength, they show that the equation of motion for the spinning charged particle should take this universal form. And in addition to the charge, there is only one free extra parameter you can add, which is nothing but the gyromagnetic ratio, G. And if you look at this equation, you realize immediately that G equals 2 is special. The second term in the second line of the equations drop out. And for a constant magnetic field background, we have this circular orbit, cyclotron orbit. And the precession of this spin is completely synchronized with the cyclotron frequency, if and only if G takes this special value. So one question is, if we throw in more and more complicated couplings with extra Wilson coefficients, is there a particular set of Wilson coefficients which we can claim is much simpler than any other possible choices? And yeah, we are trying to claim that that is actually the case. And it has some history. So let me call it old wisdom number 2. And it's the Newman Johannes shift from 1965. Yeah, they were studying the then state-of-the-art solution of a Kerr black hole. And they realized the fact that by doing some complex shift of the Minkowski spacetime, where this imaginary part is the spin vector divided by mass, they were able to use this complex shift to turn the Schwarzschild black hole solution to the Kerr black hole solution. So if you assume that this spin vector is small and you expand the Kerr black hole solution in powers of y, then of course the zeroth order by definition agrees with Schwarzschild, and you have infinitely many terms. But the infinitely many terms come with very specific coefficients. And they show that those coefficients can all be summarized in a very clean way by this complex shift. So the curve black hole is, in a sense, complicated, but in a sense very simple, in that apparently all the Wilson coefficients are fixed by some interesting, mysterious principle. Fast forward to 2010s, people did a lot of work on double copy and so on. So in a fun paper by Arkani-Hamed, Huang, and O'Connell, 2019, I'm not sure whether they were the first people, but anyway, they found the electromagnetic counterpart of curve black hole, and they called it a square root curve solution. Roughly, the idea is, I might be off by some vectors, but yeah, the rough idea is that the Coulomb electric field is, where phi is, you deform this by a complex shift of the coordinate. So after the complexification, you still use the relation, but now phi is, now things are complex valued, and you have this self-dual combination waiting for the solution, and this is phi 4 pi q . So it's not absolute value. It's a complex squared, and then taking the square root. So if you expand this potential in terms of this y, then you have some complex vector field, and you separate the real part and the imaginary part. The real part gives you the electric field, and the imaginary part gives you the magnetic field. But it's easy enough to show that away from the particular point where this guy vanishes, the vacuum Maxwell equation is satisfied in a trivial way. So it's an exact solution of some strange charged spinning particle. And it shares the nice features with the curve black hole. And well, in many ways, square root curve is, of course, simpler than the full curve in general relativity. So when we are trying to couple our massive Twistor model in an arbitrary electromagnetic background, our goal is to get the dynamical version of this square root curve particle. I mean, this solution assumes that some strange particle is sitting at the origin of your space, and you are looking at the electric field and magnetic field sourced by this strange particle. But our goal is to go a step further, and we want to examine the world line action of this strange particle coupled to an arbitrary fixed background field of in electromagnetism. So how do you go from a free theory to interacting theory? Well, you turn on some coupling term in your world line action. But if you look at it a little more carefully, there are two slightly different approaches. You can either deform your Hamiltonian so that the action takes an extra term that looks like this. Or you can try to deform your symplectic form and the symplectic, what enters the action is the symplectic potential, where I'm denoting the symplectic form by omega, which is the exterior derivative acting on the symplectic potential. And now we are assuming that the full symplectic potential is the sum of free part and the interacting part. So suppose we revisit the minimal coupling of a non-spinning particle in electromagnetism. Before introducing the background field, in a sense, this translation generator is the Hamiltonian in an effective sense. And the symplectic form is, of course, the standard one. So I'm just saying that when you turn on the electromagnetic background, you can either add its effect, try to add its effect to the Hamiltonian or the symplectic form. You can try both, but I think, well, we think it's more natural to put it on the symplectic form side, which is equivalent to the interacting term written in this way. So in quantum mechanics textbooks, they distinguish these two notions of momentum: the canonical momentum and the kinematic momentum, and you go back and forth between the two. In that parlance, this is the kinematic momentum, but and we prefer not to introduce the canonical momentum because it sort of conflicts with the gauge invariance and so on and so forth. So, yeah. We take this viewpoint. Now, it's time to turn on the spin. And again, there can be many ways to turn on interacting terms, but we will follow this line of square root Kerr particle, where we expect that all the coefficients of higher order in field and higher order in spin terms are fixed. All the coefficients are fixed. And this Newman-Johannes shift is the guiding line. Well, at least in flat space-time, the Newman-Johannes shift is literally a constant shift, although it involves the imaginary direction. So how do we do that? We are following this symplectic deformation viewpoint. So Hamiltonian is not changed. The same mass shell constraint playing the role of Hamiltonian. Well, what about the symplectic form? The free term is there. Well, actually, we are doing the Twistor model, so it's a bit more complicated than just dpdx. But anyway, the free theory has its own symplectic form. And then we want to add the field strength term there, which does this Newman-Jones shift for you. And the proposal is that given your background field strength, you split the self-dual part and the anti-self-dual part. You can always do that. And then you apply the Newman-Jones shift in a way that couples the holomorphy of the complex variable to the self-duality of this field strength. So you analytically continue this F plus with this Z coordinate and continue the anti-self-dual part with the Z bar coordinate. And we are claiming that this is the generalization of the Wagerman-Michel-Talegdi equation with G equals 2. Perhaps I should mention that we were not the first people to think about this complex shift. Slightly before we finished our free theory paper, there was a very nice paper by Guevara, maybe O'Connell, Otroff, and Vines. It's December of 2020. Anyway, the title of this paper is a worldsheet for Kerr. So they do essentially to try the same sort of Newman-Jones shift as we do. I mean, they did it first, but so just for reference, let me write down the GMOV proposal. So this is world line time integral, and they introduced this extra space-like direction. So in a notation similar to ours. And here u is just the time derivative of x. And I'm using the same y for the spin direction. And if you expand everything in powers of y, both in our model and in their model, the zeroth order agrees. Obviously, the first order also agrees, but from second order on, I don't think they agree, and we are proposing a model somewhat different from theirs. And when we were first studying their papers, we were not sure about the gauge invariance of well, not the gauge invariance, but yeah, we were not sure whether this proposal for the NJ shift is exactly what we want. And roughly speaking, the main difference comes from the fact that, you know, if you start from this expression and try to complexify things, you want the variable x both inside the function and also in this differential. And to us, it seems that they didn't really complexify these dx dx differentials and only complexify this f mu nu. And we have some doubts about their proposal. So that's why we decided to come up with a slightly different model. Well, we do believe that both models produce the same static square root curve solution. So we need a more fine-printed experiment to argue which one is better. So yeah, that's probably good enough for the comparison. Yeah, so let me add a few more remarks on this electromagnetic coupling.
Can I just ask you a question?
Sure, sure.
Yeah, I'm here.
Yeah.
So these two models differ only when f mu nu depends on x, is that right? If for constant f mu nu, it will not make a difference?
I think, yeah, I think so.
So if f mu nu depends on x, then presumably if the particle has a magnetic moment, you can couple it to in different ways, right? I mean, it will depend on the magnetic moment of the particle.
Yes.
So could these two models just differ by their magnetic moment, or you think it's more serious?
Well, I'm not totally sure. Yeah, I don't even remember exactly at which order they begin to deviate from each other. You know, both of them have you know, many powers of f and many powers of spin with somewhat different coefficients. Yeah, I suppose I should have prepared an answer for your question, but okay. Sorry, I didn't.
Okay, thank you.
So what can we do with our model? Well, to say the least, our model is fully consistent. So for one thing, we can write down the equation for motion. Well, it's fairly complicated, so we hardly expect any exact solution unless the background is constant. But anyway, let me write down the full equation of motion. I think it's my first time to write it in any blackboard. And for the z bar, it's the complex conjugate. Yeah, so they look fairly complicated. In a sense, the equations are more complicated than they look on the blackboard because you have this time derivative on the right-hand side. So actually, you have to iterate the equation many times to produce higher and higher order terms. Yeah, in practice, I think we want to solve the equation by truncating the iteration up to a certain order and get some approximation up to that point. And in the leading order truncation, they do agree with the BMT equation with G equals 2. And it's a very particular full nonlinear generalization of that minimal coupling model. So one of the obvious things we try to do with this model is to compute the observables in a binary system. So in the leading order in the post-Lorentzian approach to the scattering problem, we computed the classical iconal in the sense I explained yesterday here. Another technical element was to split the photon propagator into the self-dual part and the anti-self-dual part. They are, kind of separated, which is a fact well known among experts. So yeah, up to chi1, it's not too difficult to write explicitly on a board. So let me do that. So there can be a few consistency checks you can do. If you turn off the spin here, you reproduce the 3-level iconal for non-spinning particles, as you should. And so the y coming in here is the total spin, the sum of the two spin vectors from the two particles. It just happened that the 3-level iconal, or the equivalent Hamiltonian, was computed for gravitational binary before the electromagnetic one. And again, some of the simplification was observed there. The appearance of cosine hyperbolic or sine hyperbolic can be traced back to this e to the k dot plus k dot y and e to the minus k dot y, which are a direct consequence of the complexification of the plane wave vector e to the ikx. And to emphasize the usefulness of the classical iconal, let me remind you that, so to the leading order, this sort of expression is universal. And for practical computations, you use the form written in this second line. For the spin variables, again, this expression is universal, but since the Poisson bracket or the Dirac bracket is slightly more involved, you end up doing a computation with the formula written like this. Actually, in one of the early papers by Guevara, Otrov, Vines, they wrote down a formula that's equivalent to this one here, but I don't think they really explained where they got this from. And now we have a clear understanding of why this type of formula works in terms of the classical iconal. So I suppose I should close my talk. Yeah, so wrap up everything in 2 minutes. We show that the spherical time model and the massive Twistor model are equivalent as free theories. And what really matters is the physical phase space. That's the only physically meaningful object. And if we build up on top of this physical phase space, no matter where you start from the Twistor model or the spherical time model, you should end up with the same sort of interacting terms in your theory. Then, well, if you have a choice, then you would go for a more economical one. And to us, it's obvious that the Twistor side is more economical because it has less gauge symmetry to worry about. And so we illustrate the idea of deforming the free theory by coupling to electromagnetic background, and everything seems to work in a fairly nice way. And obviously, our next target is to couple the Twistor model minimally in an arbitrary gravitational background. But after many years, we are still not there yet. And I don't think I can explain why we are being so slow on that front, but maybe if any one of you is interested, we could talk a little more over lunch or something. Thank you.
Do we have any questions? Okay, with that, let's thank Sangmin for a very nice talk.